Next up on the docket is deep learning. Again, this is a term that you probably would have heard about a lot as well. What is deep learning? You remember this diagram, right? In this, we saw how machine learning is a branch of AI. Deep learning is a branch of machine learning that uses artificial neural networks to help computers understand and process information in a way that mimics how humans learn. Think of a neural network as a big network of interconnected brain cells called nodes. These nodes work together to analyze and make sense of data. In the past, creating really complex neural networks was difficult because computers were not powerful enough. But today, with the help of big data analytics and more powerful computing resources, we can build much bigger, more complex neural networks. And the cool thing is, these neural networks can learn and make decisions faster than humans in some cases. Reiterating that final point, this is the worldwide Google Trends data on the term deep learning. You can see it generated next to no interest for a decade post-2004. But at this point, around the end of 2014, it started taking off very quickly. There are multiple reasons for this. A possible reason could be that deep learning requires large amounts of data, and the devices that collected data by the buckets weren't as prominent as they are now in the early part of the millennium. The technique also required lots of computational power. And again, computational power and storage capacity became much cheaper as we approached 2020. We know that deep learning uses different, more complex techniques. But why would we prefer it over traditional machine learning? Performance is one of the big reasons. If we plot an amount of data versus performance graph, deep learning's line would look something like this. And this is what traditional machine learning would look like. As you can see, it plateaus after a certain level of performance and data. Keep in mind though that this is a rough graph, but the gist of it will still hold. Another major difference between deep learning and machine learning is how feature extraction is done. Feature extraction basically means identifying the variables that will help the algorithm predict better. In machine learning, most of the applied features need to be identified by an expert and then hard-coded as for the domain and data type. Example features can be pixel values, textures, shape, position, and orientation. The performance of most of the machine learning algorithms depends on how accurately the features are identified and extracted. Deep learning algorithms try to learn high-level features from data itself without the need for an expert. This is a very distinctive part of deep learning and a major step ahead of traditional machine learning. Therefore, deep learning reduces the task of developing a new feature extractor for every problem. Keep in mind though, deep learning is not a silver bullet, meaning it definitely is not the best solution for any and all situations. The main downside is that it is significantly more complex and therefore will require more processing time. This will be a no-go in case you require instant feedback. You do need to carefully analyze the problem and requirements of your application before you embark on a solution technique. We've seen what deep learning is, but how exactly does it work though? If you want to know how deep learning works, the first term you need to familiarize yourself with is neural network. Now, what is a neural network? A neural network is a system of interconnected nodes that aims to mimic how the human brain processes information and recognizes patterns. When we go through the design and working of a neural network, you'll quickly see why that is an accurate, if simple, description. This is the structure of a typical, fairly simple artificial neural network. Don't worry if it looks complex. I'm going to keep the explanation as simple as possible. Here, each circular node represents an artificial neuron. Neurons in deep learning models are nodes through which data and computations flow. Each arrow represents the connection from the output of one artificial neuron to the input of another. There are three types of layers in a neural network: input layer, hidden layer, and an output layer. A combination of these artificial neurons make up a layer of the network. After pre-processing and cleaning the raw dataset, it is first sent to the input layer. The data then moves through to the hidden layer, which is the brain of the neural network. The number of hidden layers in a neural network determines the complexity of the problem the network can solve. This particular network, as you can see, has two hidden layers. The data then finally moves through to the output layer, which gives us the required outputs. Each of these connections you see also contain a number known as a weight. In the end, what the neural network does through calculated trial and error is to determine the value of these weights. The ability of the network to determine the weights accurately will determine how well it performs. Let's see how all of these components mesh and work together. The first part is called forward propagation. In this step, as you can see from the arrow below the diagram, information flows from the input layer to the output layer. Here's how it works. Firstly, the weights mentioned earlier are randomly initialized. The data, which is now at the input layer in numerical form, is then multiplied with the weights. The multiplied values are then passed to the hidden layer. Keep in mind that the input layer has multiple nodes, and each node there is connected to each node in the hidden layer. A quick glance at the diagram on your left should help you solidify this step. At this point, each node in the hidden layer sums up the values given to it and passes it through something known as an activation function. Activation function adds nonlinearity to the network and essentially decides which of these neurons fire. It determines the output of the hidden layer. The second or any subsequent hidden layers do the same thing. The output of the hidden layer multiplied by the weights again becomes the input to the final output layer, which then applies further functions to determine the output. If it is a binary classification, meaning if the network has to decide between two choices, there will only be one output node. But if it is a multi-class problem, there will be multiple output nodes. We now move on to the second and final stage, backpropagation. Here, information flows from the output layer all the way back to the input. Since we are training our network, and this being a supervised learning technique, means we already know what the output is. So in the first step of backpropagation, the network compares the predicted output to the actual output. Since this is the first time we are performing these steps, the predicted output will invariably be different from the actual output. Based on how far off the network is from the actual output, or in other words, based on its error, the network adjusts the weights. If you look at the bigger picture, adjusting the weights will determine what input the network considers important in helping it solve the problem at hand. A connection given a lower weight is considered unimportant and vice versa. This step is performed using the chain rule in differential calculus. Now, forward propagation and backpropagation is performed multiple times, and each time the network keeps adjusting its weights until finally the network is able to solve the problem with acceptable accuracy. That, in a nutshell, is how a neural network works. It probably might be a good idea to watch this video one more time because it is very important for a conceptual understanding of what goes on behind the scenes in deep learning.